So in this video, we look at global bifurcations in dynamical systems, having considered local bifurcations in the previous video. So this lesson, is focused on transitions beyond local theory. That's local bifurcation theory. So this lesson studies global bifurcations where qualitative changes in dynamics depend on the full face space the full space geometry rather than only local linearization. So, local linearization is a simplification of a complex system, and as given by the Poincaré-Bendixson theorem, we see that such linearization is a very good approximation for complex systems as far as we can have hyperbolic equilibrium points, right? So beyond local bifurcation, let's see, what's the motivation for global bifurcation? And that means beyond local bifurcation theory, local bifurcations analyze behavior near equilibria using eigenvalues. We have examples like saddle node bifurcation, bifurcation, pitchfork bifurcation, and of course, we also came across transcritical bifurcation. So global bifurcations, on the other hand, occur when trajectories interact with distant regions of phase space. So they involve invariant manifolds. So you see, the idea of local is that if you have an equilibrium point, you are only concerned about what is happening around that equilibrium point. But then maybe you have so in the whole phase space like that, the phase space is what you have with the X and Y axis, right? Like in the whole phase space, you can have things happening at some other locations, right? So you want to put all of that into consideration. That's why we look at global bifurcations. I mean, it reminds me of the idea of local champion and global champion, right? Like, you can be the best in your locality and then you have not been tested, you have not confronted champions from other places. You feel you are the best. By the time you meet those ones, so by the time all the champions from all the local areas meet, and then we know who is who, right? So that's the kind of analogy I have of global bifurcation. So the fact that you know I mean that's the kind of thing, yeah. Global bifurcations occur when trajectories interact with distant regions of phase space. They involve invariant manifolds, separatrices, periodic orbits, and chaotic sets. So chaos is in this game. So global bifurcations depend on non-linear geometry. So non-linearity does not play here again. So all those linearization, getting eigenvalues may not work here because some of those systems don't yield to such things. So talking about local versus global bifurcations, right? Local bifurcations depend on linearization, like we saw before. X dot equals AX, and that's it. So, and then you have global bifurcations depending on X dot equals F of X comma mu for large regions of phase space. So you are not just interested in what is happening around an equilibrium point. So the key features here, you have infinite period, sudden chaos, orbit destruction, and non-local interactions, right? So let's consider homoclinic orbits, for instance. So by definition, a homoclinic orbit is a trajectory which satisfies the fact that limits of x of t as t approaches plus or minus infinity, that's infinity on both sides, gives a particular x of s, where x of s is a saddle equilibrium. All right. So in a homoclinic orbit, you have a trajectory such that as x of t tends x of t the limit of x of t as t goes towards infinity, either on the positive or on the negative side, you have a saddle equilibrium like that. So the geometry is such that the geometry leaves saddle on unstable manifold, returns on stable manifold, and forms a loop also, right? Then the importance of this homoclinic kind of orbit, which results to a saddle equilibrium as xt as t tends to infinity for xt. The importance of that is this: that homoclinic orbits are associated with chaos, infinite period oscillations, and sensitive dependence. So, and then a good example of that would be the Duffin oscillator. If you consider x dot dot plus dx dot minus x plus x cube equals 0, we can actually make this into a system of two by two a two-dimensional system by just saying x dot is y. So if the x dot is y, it means that x dot dot is automatically going to be y dot. All right. So because x dot is already y, so y this now becomes like y dot plus dy, minus x plus x cube. So if you now make y dot the subject of formula, that's why you now have x minus x cubed minus dy now because we've said x dot is equal to y. So that's the way to make a two by it's a one-dimensional two a one-dimensional second order ordinary differential equation. You can make it into a system of two of two first order differential equations. So that may be useful sometimes. So you then see this system admits homoclinic loops for special parameters. So I think the parameter here will be this delta, right? So if you have some special parameters, it can admit homoclinic loops where you then have a saddle equilibrium. We have it demonstrated right here. So let's imagine you take delta to be 0.1. Delta is a parameter, like I said, you have the two systems now, the x is y, the y is x minus x cubed minus delta y. So if you vary the delta y, you can see all of these things happening. So z naught, you have 0.01, 0.01 like that. You have the t-span and all of these things. So I'll just go ahead and, run that to see the approximate homoclinic orbit. Okay. So yeah, this is what we have like this now. So this is the approximate homoclinic orbit right here. So you see you have the equilibrium most likely is this 1 by 1 comma 0. Okay, 1 comma 0. Of course, that's clear too. So okay, if you can see that here. The equilibrium y is 0 clearly. So if y is 0, then this is gone here. So we just have x minus x cubed. So we have y is 0 and then x into x cubed, that's x into 1 minus x squared. So you have x is 0, y is minus 1, y is plus 1. So you have 0, 0, 0 minus 1, 0 minus 0 plus 1. Okay? Like that, No, that's 0, 0, 1, 0 minus 1, 0. Okay? But what we see here, the focus here is on the 1, 0 part of things. That's for the D parameter being that. So what if this delta is 1? I just want to do that and see what happens here. Okay, so so this bigger this gets, the more the fewer the spirals you have. Okay. What if I make this 10? I mean, sometimes you just want to check the system to know. So you have a kind of parabola here. So the spiral is slower or something. If I make it 100, maybe it becomes like a parabola, full parabola like that. Okay, I mean, it's this kind of line now. Okay. So, and that's why you need for special parameters, right? So we've done 0.1. What if we then try 0.01, right? So this is 0.1 now. So you have this. How about 0.01 like this? Okay. For 0.01. Aha. So you see, it's so that parameter makes, so the bigger the value of delta, the smaller the number of spirals, so to speak. So, but as that becomes smaller, if I make it even smaller, you can see the, oh, okay, wow, okay, it's even branching out in this case. So approximate homoclinic orbits now. So it's even branching out, like you have something of the nature of glasses, So 0.0001, maybe it's also gonna, okay. Okay, let me take a very small number and see what really happens. So, okay, very small, 0.00. Okay, this is just tidying up. Okay, it's like another one is forming in the center already. Okay, let me add many more zeros. This is interesting. Um, yeah, add many more zeros and see what happens. Okay, yeah, it's like everything just stabilizes around this. Okay, so yeah. Um, so at what point did we get that? Uh, okay, we still have this right here, and then this can 0.01. We have this. Okay. So, and then later it branches out like that. Okay, I mean, these are all these things go. So you want to check out how this works. So that's talking about homoclinic orbits. Then we have heteroclinic orbits and cycles. So by definition, a heteroclinic orbit connects two different saddles. So for a homoclinic orbit, you have just one saddle, right? Uh-huh. Mm, could it be that okay, well, let's just see. Okay, let's go. So a heteroclinic orbit connects two different saddles. Imagine the limits. So for homoclinic orbit, right? Well, whether as t is approaching minus infinity or plus infinity, you have the same behavior that x of s xt is becoming an x of s, which is like a saddle equilibrium. But in this case now, you have the limit of x of t as t tends to minus infinity gives a particular saddle A, as x of t as t tends to positive infinity, x of t gives a particular saddle B. So a heteroclinic cycle is a closed chain of such connections. Okay, so could it be that when the value of delta in the previous situation for the different oscillator, when the value of delta becomes like very small, that's leading to a heteroclinic orbit, that's something we want to consider. I'm not very sure about that. Okay. So the properties of of heteroclinic orbits and cycles, you have long residence near equilibria, then you have switching behavior, and you have slow fast dynamics also. We have a very good example lies in the May-Leonard computation model, where you have xi dot equals xi into 1 minus xi minus alpha xj minus beta xk. This model exhibits cyclic dominance and heteroclinic cycles. So, so you can have that as this system. So you have xi dot, it means you can have the xi dot, you can have many families of that. So if you have dx now, that's dx dt. So that means you can have x into 1 minus all that, all that, all that. And then xj, now maybe that's like your xk is like z1 or whatever you want to call that. Then dy, and then you can have all the parameters varying the way they are. And you have like some kind of initial condition. So 0 0.6, 0 0.2, 0 0.24, x, y, z, like that. Then you have your time to 0 to 200 and all that. And then you can have some heteroclinic cycling. So when we run this now, okay, see what that looks like. You have this heteroclinic cycling. Now I'm looking, what do we have any parameter? Okay, the only parameters we can then vary, where are these? Okay, the parameters have already been fixed here. Yeah, so it's same alpha all the way, so they are not varying. So yeah, that's what we have for heteroclinic cycling. Okay, so we go for 10.5, which talks about saddle connection bifurcations. A saddle connection occurs when stable manifold intersects unstable manifold. Now, you remember the idea of stable manifold? It's simply, I mean, it sounds like big English, but you have a stable manifold where the eigenvalue is negative, and you have an unstable manifold where the eigenvalue is positive. We saw that in previous videos, right? So for stable saddle connection bifurcations, we have two types. We have the homoclinic type where we have the same saddle, and the heteroclinic type where we have different saddles. So this causes global rearrangements of trajectories because you have a stable manifold intersecting unstable manifold, and then we have a stable saddle connection bifurcations. Imagine this example: x dot is equal to y, and then y dot is mu minus x squared, right? So so in that case, at critical mu, so this mu now is the parameter. At critical mu, you can have separatrices connecting. So in this case now, you have, imagine the Python code here. So mu determines what happens. So if you start with mu of 0, right? And then you have x, y is z, and then for x is y, and y is mu minus x squared here. And we have initial conditions for x and y, 0 0.1 and 0. You can vary all of that to see what happens. But we are starting with a mu of 0 0.0. So we run this now, and then we have this saddle connection like this. So let me see what happens if I make this one. What does it change? What happens? Okay, then we have this kind of shape. Then what if I have even something smaller, 0 0.01? Okay, we have this kind of thing right there. What if I make it 0 0.001? Okay, 0 0.001. Okay, it's stretching out. So as I increase this one, the formation takes more shape. So what if I just do one straight, just jump to one? Okay, we have that cycle thickening like that. How about 10? Does that do anything dramatic? Okay, it's just thickening the cycle. And then what about 100? Okay, it's thickening that cycle basically. Okay, so um some of these things border on work of art, right? So if you're interested in math art, you may want to understand some of these things, right? You may want to use them as much as possible. So like that. Okay, so let's go and talk about blue sky catastrophes. So a blue sky catastrophe is a bifurcation where a periodic orbit appears suddenly. Then In that case, period tends to infinity, amplitude remains finite, and it occurs without local warning. That is why we call it a catastrophe, right? Blue sky catastrophes. A very good example of that would be this radial model where r dot is equal to r into mu minus r squared into 1 minus r squared. This equation exhibits blue sky behavior. So here the parameter is still mu, right? So taking a mu of 0.05, and then we define the radial function, the radial model. So we have r into mu minus r squared into 1 minus r squared, that's multiplied. Then the initial condition, you just take r to be 0.1. You can vary that to see how all these things play. And then we do every other thing, and we see this blue sky oscillation. Okay, this is what the kind of thing we have. It's just the chaos appearing out of the blues. So let me change this to 0.5 and see what happens. So this is 0.5. Okay, it's straightening out. What if it's 5? Does it become like a line? Okay, it's sharpening up still. So it's more like things just change dramatically. So what if I have 50? Just straightens it out even a bit. Okay, all that. Okay, let's go small. Like this is 0. Let's say 0.05. Now we start with 0.5, right? Okay, it's just makes this like this. What if I say 0.005? Okay, okay. Now we have something switching. We have something changing over there. We have, let me go one step more and do this. We have, okay, yeah, we have that sharpening out. So, okay, what if I leave it at 0.5 and then change this one to the initial condition here to 1? What does that help? What does that change? Okay, everything just stabilizes there. What if I have 0.5 also for R? Okay, we have 0.5 for R. Okay, so you have some kind of oscillation appearing like that. What if I say 0.05 for the initial condition for R? Okay, yeah, I mean, it's basically the same technically. All right, so we go on for uh global chaos onset. So chaos arises when stable and unstable manifolds intersect transversely. So this produces a homoclinic tangle, and the consequences include infinite periodic orbits, sensitive dependence, and strange attractors. So imagine we have a forced Dolphin oscillator where we have x dot dot plus dx dot minus x plus x cube equals gamma cos omega t. This system exhibits chaotic attractors because we are talking about global chaos onset. So of course we can make this into a into a two-dimensional system by just saying uh, x dot is equal to y. So in that case now x dot dot will be y dot. So I'm sure that is yeah, that's what has been done here. So in this case now, you just have y dot is now x cubed minus x and all that. So you have x minus x cubed minus delta y because that's y dot. So this has made it to a two-dimensional system like that. So, and then we have all these things leading to a chaotic attractor. So I run this now, and then we have this. Yeah, this is really chaotic indeed. All right. So it's chaotic, as you can see that. So from here now, of course, we know y is 0 and x is also 0 because once y is 0 like this, so this is gone. Yeah. Okay, but we also have the time component of that. So we have all this. Yeah, so in summary, we see that the phenomenon, if the phenomenon is, if we have a homoclinic situation, we have a saddle onto itself and the effect is chaos. Heteroclinic, we have a saddle to saddle and we have switching. Then we have a saddle connection, we have manifold contact, which leads to reorganization. We have blue sky for infinite period and that leads to sudden oscillation. For chaos onset, we have a homoclinic tangle, and that leads to deterministic chaos, as we can see right here. So you have two homoclinics tangling together like that. Okay, so we see the conceptual roadmap in this case. You have local analysis leading to manifold geometry. So if local analysis fails, you go for manifold geometry and you have global connections, and then you can see chaos emerging. So the steps you have you identify equilibria, you compute eigenvalues, you track manifolds, you detect intersections and simulate numerically. So we have some key takeaways that global bifurcations depend on entire phase space. So for local bifurcation, you are just focusing on just some equilibrium points. So but global bifurcations depend on entire phase space, and saddles play a central role. Homoclinic structures generate chaos, and numerical simulation is essential. Small parameter changes cause major effects in this kind of systems. So we have some practice problems as usual. Solve the following problems analytically, conceptually, and when appropriate, do that numerically too. So let's show them in twos as we want to do often. So homoclinic detection, consider the system, show that 0, 0 is a saddle, find the eigenvalues, explain why homoclinic orbits may exist, simulate numerically for delta equals 0.1. So I mean you can just use the code I showed before and try to do that. So you can do the phase portraits of this one. So for 3 and 4, you have heteroclinic cycle and stable and unstable manifolds. You can work that out. Then 5 and 6, you have saddle connection bifurcation, and then you have blue sky catastrophe. So exactly what I did the other time. You want to check it again, the code. Then period divergence and homoclinic chaos. So consider a periodic orbit with period T of mu and all that. Then assume a transverse homoclinic orbit exists like that. Then 9 and 10, first Duffin system. You have this rewrite as the first order system, numerical exploration, choose a nonlinear system of your choice, identify equilibrium, compute eigenvalues, simulate trajectories, search for global bifurcations, and write a short report on your findings. Yeah, so you want to try all this out as much as possible. If you get to do any of this, you can send me what you have done. Let's see what that looks like. Okay. So with this, we come to the very end of this idea about global bifurcations. So subsequently, I'll be considering another aspect of dynamical systems. Let me know how helpful this is for you. And if there's something else you'd like me to try out, let me know. If you have subscribed, I thank you very much for doing that. If you haven't subscribed, the question is, what are you waiting for? Go ahead and subscribe and hit the notification bell so you can always get alerted each time a new video is uploaded. If you can also become a member of this channel by clicking on join. That gives us special privileges, like you get to see some videos, only you. Sometimes you get to see some videos before other people. Um, you know, there are all kinds of benefits that are attached to becoming a member. Ultimately, don't forget to comment, like, share, so that more people can have access to the great content I have going on here. Till I come your way again, keep doing maths right. Bye.